Parts of a wave. So this is where we're going to talk about a common vocabulary that we can use to describe both the physical and temporal parts of a wave. So we're going to start with the physical oscillation of any point on the wave. So this is what you might hear as the spatial part of a wave. So a periodic wave, which is generally what we're going to be talking about here, it creates simple harmonic motion at each point. So if it's a longitudinal wave, the particle movement is along the direction of energy transport. So if you look at any given point, it's going to create, in this case, a horizontal oscillation. A transverse wave, the particle movement is perpendicular to the direction of the energy transportation. So in this case, the particles are going to oscillate vertically while the energy moves horizontally. So that creates a transverse wave, which is the one we used in class. So the crest is the highest point in the wave. You can kind of picture this as a 3D image coming out of your screen where the crest is and the trough going into your screen. So the crest is the highest point and the trough is the lowest point. As that moves through time, the wavefront will actually move, in this case, I would say to the right, but it could be moving to the left as well. So the other case was longitudinal waves. So this is like putting a pulse through a slinky. Another example of this is sound. So a vibrating tuning fork will move air, and that air moves back and forth. And so that's an example of sound as a longitudinal wave. So you can see in this image, it's been depicted as little air particles, and there's these clumps where they're closer together. You could see this in the slinky as well. So those are called compressions. Now the space in between compressions, where there's not as many particles in the same area, those are called rarefactions. Alright, so here's an actual image of a wave. Alright, so this is actually what we call a standing wave, and we'll discuss these later on. But here, you can actually see a physical image of one wavelength. Okay, so at any given point in time, you've got an entire cycle. You've got 2 points at the end, and then you have 2 crests and 2 troughs when they're at the maximums. So the bit in the middle there is called a node, okay? And the 2 ends don't move in this case, all right, except for the person on the right giving it the motion. But we're going to ignore that. And then the 2 places in between the node and the 2 ends, those are called the antinodes. Now, some of you are going to not like this, but the best way to remember that that bit in the middle that doesn't move is a node is with a pun. Nodes are points of no displacement. So a wave is also an oscillation in time. So this is the temporal portion of a wave. So the period of oscillation should be familiar. This is how long it takes the wave to complete one full cycle. So if you think back to that last slide, for one of the antinodes to go all the way from being a crest to a trough and back to a crest, that time period is the period. And again, the inverse of that number is the frequency. Just like in simple harmonic motion, period and frequency are still inversely related. So you can see that what we've usually been graphing is the position, all right, as you go through this wave, but you can also do it as a function of time, all right? So the frequency is 1 over 2 pi hertz in this case, in that lower graph done in green. There's one equation from the AP equation sheet that we actually modeled today in class. So here, all right, you have basically your standard sinusoidal function. We're using cosine, and instead of doing cosine of theta, you have to take the cosine of an angle. So if I just had time in there, the units would be seconds, and that doesn't work. So to get rid of the seconds, you actually have to multiply by the frequency. So if you remember, the units for frequency are hertz, which is 1 over a second. So seconds over seconds cancels, and then in order to convert it to essentially an angle, we multiply by 2 pi, and this is because we're using frequency and not what we'll call angular frequency in the next unit. Okay, the A coefficient out front is to make your graph equal to whatever amplitude you actually have. If you're just graphing cosine, your maximum value would be 1. So in order to scale it to what you need, you just multiply by the amplitude. Now, remember, this only describes the position of a single point that oscillates with amplitude A as a function of time.